Okay, so I'm just going to start this from the beginning and skip ahead to wherever we left off in class, and then for those of you who weren't here, you'll see the whole thing. So we're going to do modeling with logarithmic data, and so you can clearly see like this follows a log pattern, and the type of log that's in your calculator, like if you want to use your lists in your calculator to do this, if you look at your calculator, it only has natural log in there. And so if we use a natural log, we'll be able to kind of see it also in our calculator. But anyway, so this data says the average salary for a church size for a pastor of a church whatever size right here. And the data is actually back here. We're going to be using it on that example. But this is just to show you, logarithmic pattern. So we've done linear, quadratic, exponential. Now we're doing logs. So you're going to have two choices. You got your natural log or log base 10. I suppose you could also do other bases as well, but we'll just be doing these two. All right, so they're telling you, I'm telling you in this problem here that there is a scatter plot with the 0.23 on it, or a log graph with the 0.23 and the 0.57. Okay, so these are selected values from a log function, and this is the format. It's a natural log function. So basically what we're saying here is when you plug in 2, you get 3. You plug in 5, you get 7. Now when I say plug in, remember you're plugging it in for x. So we're going to write two equations using this information. So when I plug in 2, so a plus b ln 2, I get an answer of 3. And then when I plug in 5, I get 7. All right, so this is like a system of equations. All right, it's a system of equations that they both have to be true at the same time, because my graph has to go through both of these points at the same time, or one after the other. All right, so we're going to find the values of a and b. We're going to solve the system of equations. So instead of using the addition method, we are going to use the addition method, but we're going to subtract. Like if I basically draw a line and put a subtraction here, you see how the a's cancel out. So a minus a goes away. So this one though, these do not go away, because this is, ln2, that's just a number. So if I have ln2 times b, I basically have 0.6693b. And then down below I have ln5, so I have 1.6b. So those do not cancel, but they will subtract. So these cancel out. I get b ln2 minus b ln5 equals -4. All right, so let's clean this up. Let's pull out the b, have ln2 minus ln5, factor out the b. So basically I have b, this is ln2 fifths, because subtraction turns into division. All right, so I'm just going to go in my calculator and take -4 and divide it by ln of 2 fifths, right? Okay, so there is my b value. So what you can do, a couple things you can do. You can store this as b, but like if you press the store button down here, right there, and you can press alpha and then letter B right there. So you see it's going to store the answer as B if you really wanted to do that for use later on. But we don't really need to. Let's see, 4.3654. We'll use 4 decimal places. All right, so now that I know B is that, actually, that is going to be useful to do that, so never mind. All right, so now that I know B, I'm going to take either of these equations. I'm just going to use the first one. I got A plus B, which is 4.3654 ln 2 equals 3. So I know that if I want to solve for A, I have to do 3 minus whatever this makes. So that's where this storing will come in handy. I could do 3 minus B, so alpha B, because that's going to be that number there, times ln 2. And there's that answer. So -0.025, we'll say 9. Okay, but I could have also done this. 3 minus, I could go up and grab this number, and I could say times ln, what was it, 2. Okay, so either way, doesn't matter. Okay, same thing. All right. So there's my A value. So my equation, here we go. I'll just write it over here. Lx equals, I got A, -0.0259 plus B, so 4.3654 ln x. So there's my equation. Now, if I had done that in my calculator, I could have also done a stat edit, and I'm going to go ahead and clear these lists and put these numbers in. So I'm going to get 2 and 5. Oops. And over here, get 3 and 7. And stat, calculate, and we'll find that linear log or natural log regression. Go ahead, I could store it, but I'm not going to need it. And so there's the same answers right there. Okay, assuming you can use your calculator, which I guess you can because, you know, who's going to know those numbers? All right, on the back side. So on the back side, go ahead and pause while or maybe skip ahead. I'm going to enter these numbers in my calculator. And this table up here is the data from the beginning of the notes for the average salaries for the pastors. All right, and so actually, you know what? I just showed you how to do that. So I'm going to go ahead. I don't really need... okay, well, never mind. All right, so let's just do it. All right, so stat, enter. Let me go ahead and put this list in. 75, 120, 250, 300, 450, 650, 900, 1500. All right, now the second list. These are already in thousands of dollars. So we got 42,000, 58, instead of entering all those zeros in there. Okay, so I want to do stat, calc, find my natural log regression, and because that's what I'm being told right here, I am going to store it into list 1. All right, and there we go. So we will write S of P equals A is negative 91.542 plus 29.9088 ln, and they used a P right here. Okay, so P is the population of the church. All right, so now using the model, what is the predicted salary in thousands of dollars for a pastor whose church is 500 people? So I'm going to go ahead and plug in, 500 should be somewhere in between these two right here. So I'm just going to do alpha trace y1 of 500. There we go. So basically S of 500 is 94.329. Actually, that would be 329. That would be 33, right? Because the 9, the 5 after it changes it to a 0, so I'd have to change that to a 3. Okay, so this is in thousands of dollars, right? So it's $94,000. So 94,330, we could say, approximately. Okay. All right, down here, this time we're going to do the same thing with log base 10, and it says the most common and preferred method to measure the sound intensity is in decibels. Like you've heard that before, like that's how you measure sound. The sound intensity, B, in decibels of a sound having an intensity I, which is in watts per meter squared, is modeled by this function. So you give me the intensity of the sound. This is your input, your intensity. And that's in watts per meter squared. All right, it will output the intensity level, and that will be in decibels. And something interesting, down here is a little fun fact. The word deci refers to 10. So the fact that the level of sound found is multiplied by 10 is a part of the formula. And Bell is from Alexander Graham Bell because he had a lot to do with sound and inventing the telephone. So decibels are named after him. All right, so this information, the sound of noisy traffic has an intensity of 1 times 10 to the negative 5th watts per meter squared. So that's my input right there. So I'm going to write these points down here. I have 1 times 10 to the negative 5 is my input. It corresponds to 70 decibels. That's my output. And the second information is that a loud concert has an intensity of 1. So that's weird. 1, and then I got 120. Okay, so again, we're going to do these by hand, but you can put them in your calculator. So we're going to write two equations with A and B basically filled in. So these things, we're going to figure out what A and B are. So I'm going to say that A plus B log of this number. So let's go ahead and change that number. 1 times 10 to the negative 5th means I have a 1, and here's my decimal. I move it back 5 places. So I'm going to have 4 zeros and a 1. All right. This equals 70. And then A plus B log of 1 equals 120. Now, log of 1. So, this is my system of equations to solve, but I notice right away log of 1 is 0, right? 10 to the 0 equals 1. So since that's 0, that immediately means that A is 120. So that helps me a lot down here. So A is 120. So I'm going to use this other equation here. I have 120 plus B log of 0.00001 equals 70. Okay, so I'm going to take 70, take away 120. I'm going to solve for B, right? So let's see, 70 minus 120, and divide that by this number right here, right? So log of 0.00001. Okay, so 10. So B equals 10. All right, and let's see. So my equation is BI equals A, so 120 plus B, 10 log of I. Okay, so human eardrum is going to burst when there is an intensity level of 1 times 10 to the 4th. So according to the model found above, what's the predicted number of decibels? So I basically want to plug this number into here. So I will get 120 plus 10 log of, let's see, 1 times 10 to the 4th. So that would be a 1 with 4 zeros. 10,000. All right, so let's figure this out a little bit. This is base 10, right? 10 to what power makes this one right here? Well, this is 10 to the 4th. So this is 120 plus 10 times 4. Okay, you can put in your calculator too, but so I get 120 plus 40. So I get my BI is B of the I right there, I guess. Never mind, let me just not put that there, because I would have to put B of that number right there. So is 160 decibels. Now in the notes, in the marked up version of the